Then our first speaker is Dick Gross from Harvard. He'll speak on rational points on hyperelliptic curves.
Thanks very much. I want to thank the organizers for inviting me. I also want to thank Peter and Barry for agreeing to speak, so I didn't pull up the age quotient too high of the speakers. And I think it's so wonderful for us to come here and celebrate Manjul's work. I'll say a word about that tonight at the formal ceremony. I just am going to speak on rational points and, in general, the arithmetic of hyperelliptic curves. It's another area of number theory that his work has really transformed. So to give you the background, let's see if I know how to do this. Okay, this is an amazing feature, by the way, where you get to see the previous slide on this screen. So I'll start with a curve over the rational numbers of genus at least 2. And when you have a curve of genus at least 2, the canonical linear series, or even genus 1 or more, the canonical linear series has no base points. At any point of the curve, you can find a differential that's non-zero. And so if you map that point of the curve to the hyperplane of differentials that vanish at the point, you get a mapping to projective space. And since the dimension of the space of regular differentials is G, that's projective space of dimension G minus 1. That's called the canonical map. And usually it's an embedding of the curve into projective space. For the generic curve of genus 2 or more, it's an embedding. But when it's not an embedding, we call the curve hyperelliptic. And in that case, you can prove that the map was actually 2 to 1, and that the image is what's called a rational normal curve. It's a rational curve of degree G minus 1 in projective space that is not contained in any hyperplane. Now, that rational curve, when the genus is odd, that rational curve can be an arbitrary rational curve, not necessarily a projective line. But we're going to be interested in studying the question of rational points on the curve C, and we'll do it under the hypothesis that there are local points on the curve C. So we'll call the curve locally soluble. That's a terminology really due to Manjul. If it has points over all completions of rational numbers. And in that case, this hyperelliptic, this rational normal curve also has points over all completions of the rational numbers. When you have a rational curve, and it has points over all completions, it actually has a global point. That's a consequence of the fact that if a quaternion algebra splits at all places, it's a split algebra. And in that case, the curve X, this image of the canonical map, is actually the projective line. And so for the locally soluble hyperelliptic curves, they're actually 2 to 1 covers of the projective line. And so we can really write them down in a very simple way. You can see every locally soluble hyperelliptic curve as a double cover of P1. Why? Well, to give the double cover, at least since we're not in characteristic 2, we're over the rational numbers, you have to write down what its ramification divisor is. And we know that the covering by the Riemann-Horowitz formula is ramified at 2G plus 2 points to get a curve of genus G. And so the ramification divisor, which has 2G plus 2 distinct zeros on the projective line, is given by the vanishing of a binary form of degree 2G plus 2. The coordinates on the projective line I'm giving is x and x prime. And that has rational coefficients, but we can multiply those coefficients by anything and get the same vanishing form. And so we can assume that the coefficients are integral. And the fact that the zeros of this binary form are all distinct on the projective line means that the discriminant of this binary form, which is a complicated polynomial and its coefficients, is non-zero. And so the hyperelliptic curve itself, which is a double cover with that ramification data, is given by an equation that looks like this. Let's see if I can use this pointer properly. Thank you, Bob. Let's try the other pointer properly. It's given by y squared is f of x prime, where this is the binary form. And but this is not an equation. X and x prime we give degree 1, y we give degree g plus 1, and then this becomes a homogeneous equation in the weighted projective plane where the variables have weights 1, 1, and g plus 1. And of course, we consider a solution the same if when you scale x by lambda and x prime by lambda, you scale y by g plus lambda to the g plus first power. Now, the weighted projective plane, when g is bigger than 0, is a singular surface, but this is a smooth curve inside of that singular surface. And every locally soluble hyperelliptic curve of genus G over the rational numbers is given by such an equation, and so is determined completely by this binary form of degree 2G plus 2. If it's not locally soluble, you have to give it as an equation in weighted projective 3 space, but we'll just work with these cases. Okay, so we have all now locally soluble hyperelliptic curves looking at us. They're given by these 2G plus 3 tuples of integers, and we'll define the height of that equation to be the maximum of the absolute values of the coefficients of the binary form. I should say that the same hyperelliptic curve can have different hyperelliptic equations. You still have to act on these binary forms by the group, basically SL2. But we're only going to work in this talk with hyperelliptic equations. Okay? And once we have the height defined, and it's clear that there are only finitely many equations of height less than or equal to x because these fi are integers, and once we bound the maximum of their absolute value, there are only finitely many integers in that box, we can define the average value of an arithmetic invariant associated to the curve as this limit where you sum over all the curves of height less than x, the value of the invariant, then you divide by the number of curves of height less than or equal to x. And if that limit exists as x goes to infinity, which is always a hard thing to prove, then we'll call that the average value of an invariant. A typical invariant we might want to do, which it's a famous theorem of Gerd-Falting's that when the genus is at least 2, there are only finitely many solutions of the hyperelliptic curve. So only finitely many values of x and x prime, such that when you put them into this binary form of degree 2g plus 2, and in that case 2g plus 2 is at least 6, the resulting value is a square. Of course, you can scale them and you get another square, but finitely many solutions up to scaling. So you could say that average, that you could take that average value, the number of solutions. I mean, you could see how many solutions does an average hyperelliptic curve have if this limit exists? Well, probably 0, as we're going to see, but we don't know that. And here's another thing you can do. You can call the proportion of curves that have some property S as the number of curves with property S of height less than x divided by the total number of curves of height less than x. A pretty naive notion. You take the limit as x goes to infinity. That proportion, if that limit exists, is some number between 0 and 1. And if the limit exists and is equal to 1, then we'll say 100% of curves have property S. Okay, so what properties would we want to study? Well, for example, here's an extremely surprising result that has emerged from Manjul's work. So we now conjecture that 100% of locally soluble hyperelliptic curves with a fixed genus have no rational points at all. So, of course, there are curves that have solutions, but 100% of these binary forms of degree 6 or 8 or 10 or 12 never represent a square in the sense of proportion. Representing a square. So that's more complicated, but we suspect that's the case when you divide out by SL2, right? This is really a statement about equations of hyperelliptic curves. Okay. We can't prove that, but one of Manjul's most striking theorems is that he can prove that a majority of such curves have no rational points, by which we mean that the lim-inf of that sequence is greater than f, and that proportion with no rational points tends to 1 very rapidly as g tends to infinity, which means that the lim-inf gets closer and closer and closer to 1. So, for example, for genus at least 10, over 99% of hyperelliptic curves have no rational points. So this is quite surprising because when you do a lot of constructions with curves, and I'll talk about that later in the talk. For example, André Wei's construction of the Jacobian of a curve over the same field. You start with a curve which has a rational point, you use that rational point to make the construction, and then you have to wave your hands around a little bit and saying, well, if I didn't have a rational point, I'd have one over some finite extension and do some descent. And I always felt that part of the proof was a waste of time. And in fact, it's absolutely essential because you never have a rational point. So that was very surprising to me. And even stronger, with Joel and I and Jerry Wang conjecture 75%, and that really means the number 3/4, of locally soluble hyperelliptic curves have no points not only over the rationals, but over any extension of odd degree of the rationals. So they obviously have points over quadratic fields because you take any x and x prime and then you solve for y. But over odd degree extensions, there are no obvious points, and we can't prove either. And if you want to know y at 75%, you should speak with Jerry. But we can prove that a positive proportion of curves have this remarkable property of no points over any extension of odd degree. And I want to try to sketch the proof of this result of Manjul's and this slightly more general result that we have in this lecture. Yes?
You have to appear exactly 75%?
Yes. Yeah, the limit exists and is equal to 3/4. That's the conjecture.
Follow-up question. Do you have any hope of proving a positive proportion do have points over an extension, some extension theologically? Can we exhibit some construction that shows that the percentage that do have is
no. I don't think
that's not so clear, is it?
Not so clear. Their Jacobians would have, in fact, they would have, their Jacobians would have rank 1, and they would have infinitely many points over odd degree extensions. And it's sort of hard to see it.
But there is a reason.
Yes. As I say, speak to Jerry. Okay. Yes.
Anyway.
I'm delighted.
When you're taking the limit, do you need to specify somehow how you weigh the different G?
No. You fix G. You fix G. All for fixed G. It's a fixed genus G. You fix G and you average over all the binary forms of degree 2G plus 2 by size of coefficients. It's a very naive type of averaging.
Although the percentages that we can prove certainly will depend.
Yes, so this thing will be basically, Manjul will show that the lim inf is greater than 1 minus a constant over 2 to the G. That'll be the result. So yeah, it depends on G, and it gets closer and closer to 1 as G gets larger. This positive proportion, we have no idea what it is. It's just positive. Okay? Now to prove these results, we have to introduce some technique that goes beyond the curve. So we're going to use what I call an arithmetic theory of pencils of quadrics, which is a famous geometric theory, an algebraic geometry over the complex numbers. So we're going to work that out and see what it does over the rational numbers. And of course, we'll have to study the connection with the Jacobian of hyperelliptic curves. So I want to talk a little bit about that theory before I get into our proof. Other questions at this point? Okay. I hope I'm not blocking the screen. It's the first time I've done it with these two screens. Manjul told me to expect these two screens. It's totally awesome. It's totally awesome. Okay. So let's do the Jacobian first. So we say two divisors, which are formal sums of points on a curve, are in the same class. And this is for a general curve if their difference is the divisor of a function. This is first, the divisors, which are divisors of functions, were first systematically studied by Abel and then Jacobi. And the points of the Jacobian over an extension of the rationals correspond to divisor classes, that is, divisors modulo this equivalence relation, which are rational over E, which means that the class is rational over E in the sense that if you conjugate it, you get something in the same class. Okay? And it's known that this is a group. I mean, divisors under addition form a group, and the principal divisors form a subgroup. So this is a functor that takes extensions of the rational numbers to abelian groups, and it's known that it's represented by an abelian variety of dimension G over Q. Namely, there's a variety associated to the curve called its Jacobian, and this is for divisor classes of degree 0, which contain the principal divisors. There's an abelian variety, it's Jacobian, of dimension G, which is defined over Q, canonically associated with the curve. And moreover, we're also going to have to study the homogeneous spaces for the Jacobian, which correspond to divisor class of degree D. If you have a divisor class of degree D, you can add to it any divisor class of degree 0 and get another divisor class of degree D. And those are not groups, they're sets, but they're acted on by this group, so in fact they're homogeneous spaces. And it's known that they're also varieties over the Q, and that the action of the Jacobian on the divisor class of degree G is a morphism defined over Q, and moreover, there's a famous map called the Abel map that takes the curve. People erroneously say to it's Jacobian, but you can't do that if you don't have any points. So it takes the curve to divisor classes of degree 1 by taking a point to this divisor, And that map is also a morphism defined over Q. Unless you think these are easy theorems, they are the foundation of the arithmetic theory of curves. And they were proved, respectively, by André Weil and Jean-Pierre Serre, two of the great mathematicians of the 20th century. Perhaps Weil's greatest achievement is showing that the Jacobian can be defined over the same field of definition as the curve. That's not an obvious statement at all. I don't know. He's not here, thank God. Giving a lecture in front of Weil was a very interesting experience. I never had this problem, but he used to go to the lectures of the young members of the Institute in Fold Hall. Then there was only one lecture room in Fold Hall. Now they're in the grand amphitheaters. It was a nice hard chairs, and Weil would sit up in the front, and the poor lecturer would start out trembling in front of Weil, and he'd get about 10 minutes into it, sometimes only 5 minutes into it, and Weil would take the copy of Le Monde he had and just sort of whip it open and start reading. In any case, Weil is responsible for this theorem, and then Serre in Group Algebraic accorded class finished it up by also studying the descent of the homogeneous spaces and the Abel map. As simple as it looks, is a complicated map in algebraic geometry. Okay, so that's the Jacobian and its homogeneous spaces. Now for hyperelliptic curves, there's a special thing that happens because there's a canonical divisor class of degree 2. If you pull back a point on this double cover from the projective line, you get a divisor of degree 2, and no matter what point you pull back, you get something in the same divisor class. So there's a canonical element which I call H in J2, and it's defined over the same field as the curve, over the rationals. And so you can translate by that point, by adding and subtracting at that point, you get isomorphisms between the Jacobian and all the even homogeneous spaces, and between J1 and all the odd homogeneous spaces. So there are really only two varieties that we have to worry about with a hyperelliptic curve, or that we want to identify: the Jacobian and what people sometimes call pick 1. Okay. Now, the homogeneous space J1 is isomorphic to the Jacobian, and this is a general theorem about homogeneous spaces for algebraic varieties, if and only if it has a rational point. I mean, if it's isomorphism, then the image of the origin on the Jacobian is the rational point. And conversely, if it has a rational point, you can map J to it by taking the origin to that point and translating accordingly. So the question of whether J1 has a rational point is related to whether it's isomorphic to the Jacobian. Now, the point J1 has a rational point if and only if that second problem we were thinking about has a solution. Namely, if and only if the curve has a point rational over some extension field of odd degree. Because if it does have a point over an extension field of odd degree, then taking the sum of the conjugates of that point gives you a divisor of odd degree, rational over Q, because it's a sum of conjugates, and therefore that divisor gives a rational point in J1. And if you have a rational point in J1, then you get a rational point in all the odd J's by translating by this hyperelliptic class. And once you get up to a large enough degree, that's represented by an effective divisor, which gives you a point over an extension of odd degree. So the second problem is whether you have a rational point on J1. And so both our problems are really studying the existence of rational points. First on the curve itself, and secondly on this larger variety that contains the curve. Okay, and in fact it's somehow for me much easier to study whether J1 has rational points than whether C does. Because whether J1 has rational points, we only have to distinguish it from J or not. If we can distinguish it from J, it has no rational points. Okay. Now, that was Jacobians and their homogeneous spaces. What is a pencil of quadrics? Well, I'll tell you what it is from Manjul's point of view, and then I'll tell you what it is maybe from Joe Harris's point of view, and you'll see the difference. So for Manjul, a pencil of quadrics is two n by n symmetric matrices with integer coefficients. That's it. Okay? So what is that from the algebraic geometry world? Well, each n by n matrix, which is symmetric, gives a quadratic form. And if you think of these as two quadratic forms on the same vector space of dimension n, then in the projective space of that vector space, they give quadric hypersurfaces. And the pencil of quadrics are the different quadric hypersurfaces that you get, which are linear combinations of those two. And they sweep out a bunch of quadric in projective space, and their common intersection is called the base locus of the quadrics, which is just the points which are zero on both quadrics. Now, associated to a pencil, you get a discriminant form, which turns out to be a binary form of degree n, where you take the discriminant of this matrix. Now, remember, the discriminant is just a sign which is related to n, times the determinant of the matrix. So if you thought of the determinant, it wouldn't be far off. We'll see why you take the discriminant a little later. That gives you a binary form. And we say the pencil is generic if this binary form has a non-zero discriminant. Okay, what does that mean in Joe Harris's world? It means that the intersection of these two quadrics in projective space is a non-singular variety of codimension 2. Quadrics themselves are fairly simple varieties in projective space because they're homogeneous. A group acts transitively on them, the orthogonal group. But once you take the intersection of two quadrics, it becomes quite complicated, and it depends on the pencil. And we want to make a hypothesis on the pencil so that intersection is non-singular. And that's the same hypothesis, is that this discriminant polynomial has distinct roots. Okay. Now, if we took a vector space where the dimension was 2g plus 2, the discriminant polynomial would be the sort of thing that gives us a hyperelliptic curve of genus G, right? Because that comes from a binary form of degree 2g plus 2, and it has non-zero discriminant. So when we have a generic pencil of this dimension, so two symmetric matrices of degree 2g plus 2, such that this polynomial has distinct roots, then we get a hyperelliptic curve. So that's one variety we're going to associate to the pencil, a hyperelliptic curve. The second variety, which is just as important, is called the Fano variety of the base locus. I call that P. So that consists of all the linear subspaces in this vector space of dimension 2g plus 2, which have dimension g, and are isotropic for both bilinear forms A and A prime. What does that mean geometrically? Geometrically, that means that it gives a projective space of dimension g minus 1 inside of the base locus, right? Because if it's isotropic for both quadrics in the pencil, that means it's contained in their intersection. And so one's looking, so this is a generalization of a Grassmannian, which are the linear subspaces of projective space. Here are the linear subspaces. You can frequently do the linear subspaces inside of a quadric. That's also a homogeneous variety. But if you take the linear subspaces in the intersection of two quadrics, that's an interesting variety called the Fano variety. Okay. Now, the miracle is that we're going to define an action of this hyperelliptic curve on this Fano variety. I'll do that for you. That's the theory of quadrics. And that turns P into a homogeneous space for the Jacobian of the curve. So from a pencil of quadrics, you not only get a hyperelliptic curve, but you get a homogeneous space for its Jacobian. So let's see how that goes, because that's a beautiful geometric construction. You can find all of this in the last chapter of Joe Harris's book, An Introduction to Algebraic Geometry. All right, so let's see what a point on the curve is, what a point on the Fano variety is, and let's see what the action is. So the equation of the curve is this. So what's a point on the curve? Well, it's a point on the projective line, A and A prime. That gives us X and X prime. So that gives a quadric in the pencil, because the projective line is what's parametrizing the different quadrics in our pencil. And what does this Y give? Well, it's a square root of the discriminant of that specific quadric. Now, the discriminant tells you when the two different families of maximal isotropic subspaces, where they're defined. They're defined over the square root of the discriminant, that extension. So to take a square root of this discriminant is picking out one of the families of isotropic subspaces of dimension g plus 1. You know that on even dimensional quadrics, there are two families of maximal isotropic subspaces. And the point on the curve tells you a quadric and one of the two families. The famous example, which is the reason why there are two families, two different components of maximal isotropic spaces. If you take quadrics in two-dimensional space, they have two distinct isotropic lines. And so in projective space, P1, it gives you 2 points. And we're picking one of those points. Okay. The point in the Fano variety, which I'll call X, is a subspace of dimension G, isotropic for all the quadrics in the pencil. Now let's define the action, this point on the curve, on this point in the Fano variety. Well, we have an isotropic subspace for all the quadrics, so it's isotropic for this quadric, and we've picked one of the two families of maximal isotropic subspaces. And each isotropic subspace of dimension G is contained in exactly 2 isotropic subspaces of degree G plus 1. And we've picked one of the families. So we get an isotropic subspace of degree G plus 1, which contains our isotropic subspace with codimension 1. But it's only isotropic for this specific quadric, not for the other quadrics in the pencil. So now restrict some other quadric in the pencil to that big space of dimension g plus 1. It already vanishes on this hyperplane, which is a common isotropic subspace. And when you have a quadric that vanishes on a hyperplane, it has to be the product of two linear forms. So it vanishes on some other hyperplane. Call that other hyperplane x prime, or x star. Well, x star is then isotropic for everything in the pencil because it's contained in y, so it's isotropic for this quadric, and it's isotropic for this quadric, so it's isotropic for all the linear forms. And that's a new point in the final variety. And you can see that if you do this twice with the same value of e, you get back to x. So that each point on the curve gives an involution of the final variety. And I call that pi e of x, x star. And you have to prove that that's a morphism, etc. But that's done by the algebraic geometers. So the miracle of quadrics is that this hyperelliptic curve acts on the final variety. Now, Jerry Wang in his thesis, a beautiful thesis, took this action and turned it into an action on the Jacobian. And I like to think of homogeneous spaces for Jacobians as cosets in an algebraic group disconnected where the identity coset is the Jacobian. Because that's really what a homogeneous space is. It's a coset. Where for some subgroup, right? The subgroup acts transitively on it, but you don't have any obvious point on the coset. So an example of that is if you take the Picard variety of the curve, which has an infinite number of components, and you divide it by all multiples of this class of degree 2, then you're left with a variety with two components, j and j1. But there's an addition law, namely, if you add 2 points in j1, you get to j2, then you subtract off this h, and you get back to j. So this is an algebraic group with two connected components, right? Where the identity component is the Jacobian, and the non-trivial component is j1, and that's the homogeneous space. Okay? And if you think about it, you have minus 1 on a group. And if you have two components, the component group is z mod 2, so minus 1 stabilizes j1. And C, we saw, is a subvariety of j1 via the Hobble map. And you can prove that minus 1, when it stabilizes j1, and it also stabilizes the curve, and it acts as the hyperelliptic involution, taking y to minus y. So that's the theory of just the curve. Now let's put the final variety in. So we take the final variety associated to a generic pencil. Let C be the associated hyperelliptic curve. Then Jerry proves in his thesis that there's a group, algebraic group, commutative algebraic group, with 4 connected components, which contains this group with index 2. And the 0 component is j. The first component is the final variety. The second component is j1. And the last component is another variety, which we're going to see is isomorphic to the final variety. It has the structure of a commutative algebraic group, which gives P the structure of a homogeneous space for the Jacobian. It contains this with index 2. And the component group is Z mod 4. So that's stabilized. So J1 is in the 2 component. So it's stable under minus 1. But minus 1 takes this component to that component, and that's the isomorphism. Okay, so that this all fits together, this final variety fits together with the curve in this commutative algebraic group. So to give you the addition law, I can tell you what the generators of this subgroup are on this coset. Right? It's of index 2, so it's just a subgroup acting on the coset. And the generators are coming from points on the curve, and they're elements in J1. And if you add a point to the final variety x, you get into the component I call P prime, and that's minus what happens when you apply the involution of the hyperelliptic conjugate of the point to x. And if you add a point to minus x, that's the involution applied to x. So you should think of the involution associated to a point on the curve on x as E minus x in this amazing algebraic group. I should say that the complex algebraic geometers had studied the final variety, and for them it was the Jacobian of the curve. It was a miraculous algebraic construction of the Jacobian of the curve. Right? And Miles Reed did that in his thesis, and Ron Donaghy wrote a beautiful paper on it. But that's because over the complex numbers, the final variety has a point. Not a canonical point, but a point. And one of their problems of writing down the addition law was they had to choose some point. And they chose the point very intelligently, but not as good as this. Jerry shows the group is completely canonical. And the action of the Jacobian on the final variety, when you work it out from this, is the divisor d minus e is first you apply e to the point, then you apply d to the point. And, of course, you have to check that the principal divisors act trivially. So you get an action of the Jacobian. Okay, now Joe likes to call the final variety pick 1/2. Because if you look at this group and you multiply by 2, it takes the final variety to J1, so you have a morphism from the final variety to J1, and it takes J1 to J. So this is like, a pick 1/2. And these maps have degree 2 to the 2G because if you translate by a point of order 2 in the Jacobian on the final variety, it has the same image in J1, and likewise here. So you get coverings of degree 2 to the 2G. Now, one thing I want to stress is that pick and pick 1 and pick 0 are canonically associated to the curve. To get a pick 1/2, you have to pick a pencil of quadrics with the right discriminant locus. So that's not canonically associated to the curve. But if you do have a pencil of quadrics, you get this pick 1/2, this covering of J1. Okay, enough background. Let's go on now to the proof. Now, in Manjul's world, you always like to have an integral group acting on an integral representation and study the orbits, right? So that's related to this pencils of quadrics, because if you take this group SL2 plus 2G plus 2 modulo this element in the center, mu2, that acts on symmetric matrices in the usual way, and it preserves this discriminant form because that's basically the determinant, and the determinant of G is 1. Right? I can divide by mu2 because if I have -1 here and -1 here, I don't change A. So I have a group action on a representation. It's the 2 times 2 copies of the symmetric matrices of degree 2G plus 2. Really, you have a larger group acting. You should have the group SL2 acting here and SL2G plus 2 acting here. But we're just going to do that just SL2G plus 2 action. Now, if you started with a hyperelliptic curve, you might ask, can I find a pencil of quadrics such that the discriminant of the pencil gives me this binary form? That's not obvious at all. And what's so cool about this representation, and I think it's the most interesting representation that's been studied so far in the context of what Manjul's been doing, is that it has a very simple ring of invariance. It has a polynomial ring of invariance. In fact, the invariants are just the coefficients of that binary form. They all have the same degree, 2G plus 2. There are 2G plus 3 of them. They generate the ring of invariance. But it does not come from Windberg's theory. And consequently, there is no section. Namely, you might have a perfectly rational point in the geometric quotient, where you just specify the values of that binary form, which did not come from an orbit. And so you may not be able to solve for A and A prime such that the discriminant of XA minus X prime A prime is your binary form. And if you can't solve for it, then you can't find this variety P or anything else. All right, if an orbit does exist, if you can find A and A prime, then you get a final variety and this covering of degree 2 to the 2G of J1. Now, here's another great thing that Manjul found. We were fooling around with this and we didn't understand when there was a section and everything else. And he found an amazing formula if you have a rational point on your curve. He shows that an orbit always exists, and not only does an orbit exist, a canonical orbit exists with some remarkable properties. So, from a rational point on the curve, we choose an equation, we use the action of SL2, Peter, to move that point to 0, so that the coordinates of x and x prime are 0 and 1, and therefore, to say that this is the rational point says that this coordinate f2g plus 2 is c squared. Okay? Now, with that hypothesis, that namely just one of these coefficients, this last coefficient is a square, we can construct an orbit. And not just an orbit, a canonical pair of matrices. It's even better than an orbit, such that the discriminant of the pencil of quadrics is the binary form, and such that the final variety has a rational point such that 2 times it is this divisor of degree 1. Okay? What is that? Well, you have to see the paper. The matrices get larger and larger, but he has a way of writing them down thanks to LaTeX. But I'll show you what it looks like if G is equal to. Here are the matrices. Here's A, here's A prime. They're 6 by 6 symmetric matrices. What do the matrices involve? Well, the coefficients of the binary form, right? There they are. And we didn't use F6 because F6 is replaced up here by the square root of f6, which is c. If we didn't have that square root, we couldn't do this. Okay. Now, why is there a rational point? So we take this pencil, and if you miraculously take the discriminant of x times this minus x prime times this, and you actually calculate that determinant, which I don't advise, you will get this original binary form of degree 6. But even more remarkably, it has a rational point, because look, if you take the subspace spanned by E2 and E3, that's isotropic for both quadrics in the pencil. That's a two-dimensional subspace, okay? Moreover, why does it have a rational point with 2x equal E? Well, here's the maximal isotropic subspace of dimension 3 that's picked out by the point E on this quadric. And you restrict that to this quadric, you just get the quadratic form minus x squared, which is the square of a linear form. Right? Or it's, yeah, and so, well, it's constant times the square of the linear form. And so that shows that E fixes this point x, which says that E minus x is x, which means that 2x is E. Okay, so you not only get a final variety, you get a rational point on the final variety, and 2 times it is your original point on the curve. But in general, there are necessary conditions for a binary form to come from an orbit, and we work those out in our paper. So here it is over the rational numbers. If the discriminant, which we're assuming is non-zero, and the leading coefficient is non-zero, and you can arrange that, some of the matrices in the pencil have non-zero determinant, we take the extension of the rational numbers generated by a root of this polynomial f of x1, which is a separable polynomial with leading coefficient f0. Okay? And then the condition for the existence of an orbit over the rationals is if this f0 lies in the norm of elements from that finite extension times the squares of rational numbers in Q star. Okay? For example, if f0 is 1, which is the cases we had done before, you always have an orbit. So here's an example of a binary form for which there is no orbit, no pair of symmetric matrices. I did the simplest case of a binary form, which is genus 0. But you can see even in genus 0 there's a problem. Because why is this? Well, the extension L, in this case, is the Gaussian numbers. The norms from the Gaussian numbers are all positive. The squares of rational numbers are all positive. And the first coefficient is minus 1. So it's not in the norms times the square. In fact, there are no orbits over the real numbers here. Same argument. In that case, the algebra L is the complex numbers. Okay. And even when a rational orbit exists, if you do a more detailed analysis, you don't even always have an integral orbit, because you need a certain ideal class that's determined by the binary form to be a square. And there we use a lot of the beautiful results in Melanie Wood's PhD thesis. If you have a binary form, then following Birch and others, you get a ring, which is of degree 2g plus 2 over the rational numbers, and that ring comes with a certain number of canonical ideal classes, because the vanishing of that binary form defines a subscheme of P1, and you can pull back the line bundles O of 1 and O of 2 and O of 3 to that subscheme to get some projective modules. So a certain ideal class in that construction has to be a square. So in other words, it's difficult, given a binary form or a hyperelliptic curve, to be able to find a pencil of quadrics that matches it. Okay. Now, the fact that an integral orbit exists with some remarkable properties when the curve has a rational point turns out to be the key in Manjul's proof that most curves have no rational points, as I'll show you. But first, let's do the theorem that Jerry and Manjul and I show. To show that no points of the extension of odd degree, we have to distinguish J1 from J. And these varieties become isomorphic over the algebraic closure, so we need a really arithmetic invariant of the varieties to distinguish them. And we're going to use their arithmetic fundamental group. And in fact, we don't need the whole arithmetic fundamental group, thank God. We just need the maximal abelian 2 quotient of that fundamental group, which are the series of 2 coverings. And we're going to compare what we call locally soluble 2 coverings of J1 to locally soluble 2 coverings of J, and show that they're frequently not the same. That'll distinguish the varieties, therefore J1 has no rational points, etc. Okay, what's a 2 covering? Well, it's the sort of thing we've seen already. It's a homogeneous space together with an unramified cover, an étale cover of the Jacobian, such that when you translate by points in the Jacobian and then you apply the map, you get the map where you add 2 times the point in the Jacobian. So all the maps that I had previously from the final variety to J1 and from J1 to J are 2 coverings. And again, the preimage of 0 gives a homogeneous space for the 2 torsion in the Jacobian, because if pi of f is 0, then the only way you could translate it to get another thing where pi of f is 0 is by a 2 torsion element. So these 2 coverings all have degree 2 to the 2g. And the simplest example is just the isogeny multiplication by 2, but another example is given by this covering we saw in the Picard variety from J1 to J2, and then making an isomorphism with J. By the way, in this covering, the homogeneous space for the 2 torsion is pretty famous, because those are the points such that when you multiply them by 2, you get the hyperelliptic class, and those are called the Weierstrass classes. They're generated by Weierstrass points. Okay. Now, you can also define 2 coverings of J1. We didn't really need the addition. We didn't need a group in J. We just needed to be able to translate by points in J here. So if you take the same condition for J1, where you take homogeneous spaces that map to J1 with this property, we'll call those 2 coverings of J1. They have the same property, except there's no canonical point over J1 to take the fiber. Okay. Now, we call a covering locally soluble. Whoops, let's go back. Oh, here it is. We call a covering locally soluble if this variety has points over all completions of the rational numbers. It might not have a rational point, but all completions of the rational number. The covering has to be defined over Q, but it has to have points over all the completions. And it turns out there are only a finite number of these 2 coverings which are locally soluble up to equivalence, and they're the geometric realization of elements that are called in the 2 Selmer group, a cohomology group which measures certain 2 torsors for the 2 torsion in the Jacobian, and this standard isogeny is the identity element in the 2 Selmer group. So it's a finite group. And the locally soluble 2 coverings of this J1 form a finite set for the same reason, which we call the 2 Selmer set, but it might be empty. There's no obvious covering like this one, or J1 to J. And it turns out, after some analysis, that they all come from integral orbits in our representation. I mean, not all the 2 coverings do, but the locally soluble ones come from integral orbits in our representation, and the covering is given by the final variety of the pencil quadrics. So that we have a representation theoretic analysis of when we have locally soluble 2 coverings of J. In particular, if you cannot find a pencil quadrics associated to your hyperelliptic curve, you don't have any 2 coverings of J1, and J1 is not isomorphic to J, because you have a 2 covering of J. Okay? Now, the integral orbit that Manjul constructed from a rational point on the curve, this canonical thing, is certainly locally soluble because it has a rational point. If it has a rational point, it has points over all completions. But it's better than that, because, as I said, it has a point over the rational point on the curve. And if you look at this nice diagram where I have these 2 maps, this is the Abel map, this is the 2 covering coming from a pencil of quadrics, and I take their fiber product, right? I get a 2 covering of the curve C, namely a 1-dimensional subvariety of this final variety consisting of all the points in the final variety, which when you map to J1 land in C. That's what the fiber product is, right? That's how you construct abelian extensions of curves in the classical theory. You take isogenies of the Jacobian, you make the fiber product. Now here we don't have a map from the curve to the Jacobian, just to J1, so we take these 2 coverings. And in Manjul's case, the fact that we had a point over the point in the curve means that this curve in the final variety has local points at all places, which is very strong condition. You see, and that's, by the way, I don't like this terminology very much, but Michael Stoll and others call these elements fake 2 Selmer sets. I don't know why it's fake. It's better than being in the 2 Selmer set. It's a distinguished element in the 2 Selmer set where you not only have local points here, but you have local points here. And the hard prime is the prime 2. Because in the case of the prime 2, when you have local points here, they map to a subgroup of J1. Well, J1 isn't a group, but you pretend it is. The subgroup of J1 that has index 2 to the G. And the chance of that containing a point of this, 2-adic point of this curve is very small. And so his covering is really remarkable, even among elements in the 2 Selmer set.
Is that the same? Responsible for the same 2 to the G?
Yeah. We're going to get there. It's the prime 2 that does all the work. In all these cases of rational points on the curve, which started with Poonen and Stahl, and then Jerry and Arrow have a theorem, and in this theorem, the prime 2 plays an enormously important role. Thank God we're not over a function field. Okay. So I want to point out that this curve is very difficult to construct unless you had the theory of pencils of quadrics. Its genus is given by this formula. So, for example, when the curve C has genus 2, its genus is 17. And I remember being very struck by this because I have a wonderful graduate student who's at MIT now, Cheng Tsai, and he was working out the genus 2 case of this, and he kept saying to me, but I'm getting a curve of genus 17. I mean, Mathematica says it's genus 17. But that's because he was looking inside this variety instead of its image down in J1. And to construct this curve, I have no idea how you do it other than to take the fiber product of this diagram. It's certainly not a hyperelliptic curve, for example. Okay, now here's the argument on one side. So we use the geometry of numbers, then we look at the orbits in this integral representation of bounded height. We try to calculate the number of those orbits of height less than x. And since those orbits correspond to elements in the 2 Selmer set, if we can bound the number of orbits of height less than x, on average, we'll be bounding the average size of the 2 Selmer set. And we show that average is less than or equal to 2. 2 turns out to be the Tamagawa number of that group, SL2G plus 2 modulo U2, the group acting on the representation. Okay, but we have 2 obvious coverings of J, 2 different elements in the Selmer group. By the way, the reason this is a different element in 100% of the cases is that the torsor for the 2 torsion corresponds to the Weierstrass points, and it's extremely difficult for a general hyperelliptic curve to have a Weierstrass point over Q because it would require that binary form of degree 2G plus 2 had an odd factorization over Q, and by Hilbert's irreducibility theorem, that never happens. And consequently, we get at least of order 2 in the Selmer group, and then using results of the Duchisters on signs of the functional equation, we show that the average order of the 2 Selmer group is greater than 2. We think in this case the average order should be 6. But we don't know that, but at least it's greater than 2. And these 2 results show that frequently J1 is not isomorphic to J. So that's the theorem that will appear in a paper in JAMS. Now, Manjul has to work harder because he counts the number of integral orbits of height less than x with his special property by multiplying this estimate you get from the geometry of numbers by the densities of local orbits with points in this curve for all places V. And as I say, the key place is V equal 2. And using that density argument, he shows the lower density of hyperelliptic curves of genus G with no rational points is at least this. I think you could even make that more precise, but at this point, since we expect the density to be 1, let's wait until we prove that. Okay, now, let me finish by asking, what is so special about 2 coverings? Why are we doing all these things at the prime 2? When Manjul and Arrow attacked elliptic curves in their Selmer group, they did 2, they did 3, they did 5, they even did 4. Why are we stuck at 2? Well, 2 is very unusual in the hyperelliptic case. Because if you take a hyperelliptic curve with this equation, you take the extension of the rational numbers generated by the 2 torsion points, well, they just come from roots of this, combinations of roots of this binary form, and if the first coefficient is non-zero, that's just the splitting field of this separable polynomial. Oh, right? And the splitting field, the Galois group, is certainly contained in the symmetric group, 2G plus 2. So you're getting an extension where the Galois group is contained in the symmetric group. Now, on the other hand, if you take a general curve of genus G, and you take a general prime number, and you look at the Galois group generated by the points of the P torsion, you'd expect it to be the full group of symplectic similitudes. That would be a generalization of Sayre's theorem for elliptic curves. Because the only structure on the P torsion for a general curve and general P is the Weil pairing. Right? And so, if we were lucky, this is the group we'd get. In particular, for P odd, on a hyperelliptic curve, we'd expect this big symplectic group. And this symmetric group is a tiny subgroup of this symplectic group at the prime 2 for the genus at least 3. and the index goes to infinity as with G. So we're working on a prime where the 2 torsion is much simpler than all the other torsion on the curve. And that, in fact, the fact that this Galois group is a symmetric group, this is a reflection group, right? I mean, it's the Weil group of type A. And in the cases that Manjul and Arl were able to do in the elliptic curve case, accidentally the group GL2 of 2 and GL2 of 3 and GL2 of 5 are very closely related to reflection groups, complex reflection groups in the case of 3 and 5. And it doesn't happen for GL2 of 7. So maybe that's one reason that the prime 2 plays such a big role. So to finish, I want to say that hyperelliptic curves originated in the work of Niels Abel, I mean, for Abel, really, a curve was a hyperelliptic curve. It wasn't a curve anyhow, it was an integral, but he was doing integrals on hyperelliptic curves. And those were in papers that he submitted in the 1820s, and unfortunately were not published until after his death because none of his contemporaries could take the trouble to read them. But after he died, he became quite well known, and in the next generation, Hermite made a beautiful comment about Abel's work in his treatise on elliptic functions, and he said, Abel a laissé aux mathématiciens de quoi s'occuper pendant 500 ans. 500 years. He gave us enough to think about for 500 years, which I think is true because we've been thinking about it for 200 years and we're still not there yet. So, in my humble opinion, I think the same can be said about the work of Manjul. He has opened up a huge area of mathematics that people will be thinking about hundreds of years from now. Thank you very much. Yes, Dorian.
Yeah, on your result on getting the positivity, there's no point about extension. You say you don't know what the constant is, but is it effective? Is it extensible effectively?
I don't know. Yeah.
It's pretty small.
It's nowhere near the correct answer. Suffice it to say, we're very, I'm not an analytic number theorist. I'm really sorry. I'm not an analytic number theorist. I feel you either get the right answer or you just say, I don't know. So in this case, I don't know. Peter.
In relation to the Manjul obstruction of this rule, you have an obstruction to rational.
So there's some relation and there's some reason to believe that may be the only obstruction for curves, with locally soluble curves. We don't know. In this case, we do. Again, I don't know how typical hyperelliptic curves are of the story. We can write down the general hyperelliptic curve, which is locally soluble. One of the theorems of Joe Harris and David Mumford is you can't write down the general curve of genus G. The moduli space is not rational. So I don't know how much this will be able to be pushed. Jack Thorne has done some beautiful work on non-hyperelliptic curves of genus 3, which are quadrics in the plane, which you can write down, but it's more complicated. And we'll just have to see. Sure.
Yeah, so can this proof, does this proof already give, or could it be adapted to give independent proof of faulting theorem for hyperelliptic curves, or does this all depend on faulting theorem?
No, it doesn't refer to faultings at all. It's completely independent of all the work on the Tate conjecture, etc. But it doesn't say that a large number of hyperelliptic curves have an infinite number of points. I mean, it could. It still would be average, of a proportion of them would be very small. But it's only in proportion. So, yeah, positive proportion of no points. So that's a step in the right direction.
It's not a result talking about the average number of points.
No. And it's completely independent of his analysis, etc. Just
a result saying something about average number of points?
Not yet. Good thing to work on.
The